Hi, welcome to video lecture 3.2 of the SAGE-based course on Monte Carlo methods. I'm Raz. We will be covering the topic of independence in this video. Independence. We say two events, A and B, are independent if probability of A intersection B is equal to the probability of A multiplied by the probability of B. So intuitively, A and B are independent if the occurrence of A has no influence on the probability of the occurrence of B and vice versa. So let's look at an example. Suppose we flip a fair coin twice and let event A be the first flip being a head, and let event B be the second flip being a head. Then the probability of A is half, the probability of B is also half. Because flips are independent, what happens on the first flip does not influence the second flip. So probability of A intersection B is simply equal to probability of A times probability of B. That's half times half, which is 1/4. Let's look at the second example. We can generalize this by saying that we flip a coin with an unknown probability parameter theta. So theta is some parameter, some real number between 0 and 1. It's in the unit interval 0, 1, but we don't know what it is. And now we flip this coin twice, and the coin is made so that for any flip, the probability of heads is going to be this parameter theta. Okay? And the probability of tail clearly has to be 1 minus theta to satisfy the axioms of probability. So now take the same events as before, where event A is the event that the first flip is heads, and B is the event that the second flip is heads, just like in the previous example. Now because the flips are independent, once again, how we toss the first coin has very little to do with how we toss this coin the second time, or how we toss another coin of the same type. So because the flips are independent, probability of A intersection B is equal to theta multiplied by theta, which is now theta squared. If we take event C as the new event that the second flip is tail, then probability of A intersection C is also equal to probability of A multiplied by the probability of C, which is theta times 1 minus theta. Okay. So the second example is basically the same as the first, except instead of saying that the coin is fair, we say we have no idea what the bias of the coin is, so we're going to call this bias, namely the probability that it comes up heads, as the unknown parameter theta. Okay. Now the next example, we roll a fair die twice. The face of the die is enumerated or numbered 1, 2, 3, 4, 5, and 6. Now let A be the event that the first roll is 5, and B be the event that the second roll is 1. Okay, so then probability of A is 1 over 6, and probability of B is again 1 over 6, because we're tossing these, the first time we toss the die has nothing to do with the second time we toss the die. Okay, they're independent again. If the two rolls are independent, then the probability of A intersection B is 1 over 6 times 1 over 6, which is 1 over 36. So this is a good time to pause the video and look at this. You try. This is a very nice video from Khan Academy. So now if I click this, it's going to be a video inside a video. Okay. And let's see if this plays. Alright, so you can listen to Khan go on about it, so you can launch this video from your Sage worksheet, not this video of the Sage worksheet. So please listen to it. It's quite a good video. It's about 9 minutes or so long, and you're going to get a very nice idea of the tree diagram that he draws on explaining how these pairs of outcomes come out. So it's quite a good idea, okay, to go through this. So the next topic is going to be conditional probability. So conditional probability is perhaps one of the most important definitions and ideas in probability. Suppose that we are told that the event A with probability of A being more than 0 occurs, okay, and we are interested in whether another event B will now occur. The sample space has essentially shrunk from omega, or the full sample space, to A, the thing that just occurred. Right? The probability that event B will occur given that A has already occurred is defined by probability of B, this bar here, A, is probability of B given A. That's how this is pronounced. The probability of event B occurring given event A has occurred is equal to the probability of B intersection A divided by probability of A. So in other words, all we mean by the conditional probability of B given A, which is the left-hand side, is the division of the intersection of B and A's probability by the probability of the thing that just happened. Okay, it's as simple as that. So in a Venn diagram, here is the full sample space capital omega, here is the event A that just occurred, and here is the event B. So given that A has occurred, we are interested in what's the probability of B also occurring on top of A, right? So that's this place where the B and A intersect is A intersection B, and so that goes in the numerator and the probability of A goes in the denominator. So we can understand this by noting that only the outcomes in B that also belong to A can possibly now occur, given that A has occurred. And since the new sample space is A, we have to divide by P of A to make probability of A given A equal to 1, right? So if the two events A and B are independent, then probability of B given A is simply probability of B intersect A divided by probability of A. Due to independence, the numerator just breaks into the product. Probability of B intersect A given A and B are independent is simply probability of B multiplied by probability of A. Now probabilities of A cancel upstairs and downstairs, giving us probability of B, which really makes sense because all that says is the probability of B given A is simply the probability of B when A and B are independent. So that means the occurrence of A has no influence on the probability of the occurrence of B because A and B are independent in that case. So let's look at some examples again. Let's go back to this rolling a 2 fair dice experiment. Hopefully you've seen that YouTube from Khan Academy and got a better sense of the sample space and the tree diagrams and assigning the probability 1 over 6 times 1 over 6, namely 1 over 36 to each of these 6 times 6, 36 possible outcomes. So now let event A be the sum of the dice is 6. Okay, so that means the first die could be 5, the second one could be 1, the first is 4, the second is 2, both are 3, the first is 2, the second is 4, the first is 1, and the second is 5. So this is A. A is the event that the sum of the two rolls is 6. Now let B be the event that the first die is 2. Okay. Now how many ways can we get a 6 out of 2 dice? That's what's depicted in this picture. Okay, where we're plotting the outcome of the first dice this way and the outcome of the second dice that way. So A is simply the event, which is nothing but the set of outcomes. Here outcomes are denoted by ordered pairs because it's a rolling 2 dice experiment, so we've got these ordered pairs. So 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1. So A is this set of outcomes. Okay, and clearly probability of A is 1 over 36 plus 1 over 36 and so on. Because why is this 1 over 36? Well, it's because the first die and the second die's rolls are independent, so we simply multiply the probabilities, which is 1 6 times 1 6, which is 1 over 36, and since the dies are fair, we get 1 over 36 for each of them under independence, and the summation is there because these are mutually exclusive outcomes. They're pairwise disjoint outcomes, so we can add their probabilities. That's why this addition is there. So and then probability of A is simply 5 over 36. Now, what are the outcomes for the second dice? Well, the second die can have 1, 2, 3, 4, 5, or 6, while still having 2 as the outcome of the first die. Right? So that is B. B is this blue stuff, right? So B is the event which contains all these possibilities here, these outcomes here. So now finally, A intersection B is this is A and this is B. We intersect them. Well, there's only one thing here, 2, 4, where the first die is 2 and the sum is 6. So that's all you're doing here. So probability, so B intersection A is simply 2, 4. Probability of B intersection A is 1 over 36, because that's 1 out of these 36 equally probable outcomes. And finally, probability of B given A is probability of B intersection A over probability of A, which is 1 over 36 over 5 over 36, which is 1 over 5. So let's look at this result in terms of what we said about the sample space shrinking to A. Okay, so that's what's happening. This is A. The sample space with all those 36 possibilities have now shrunk to A because A has happened. And then on top of that, this is the only thing that is in the intersection upstairs. So this is a good time to pause the video, and we'll move on to the next topic called Bayes' theorem.